Let's get started. Names, please. Ian, Billy, Kane, Macho, Kramer, Karopinski, Barbara Lopez, Brendan Lopez, Homberg, Martin, here. Reed is here. Retzlaff, Richie, and Yakashenko. Here. Homberg is here. Macho is here. Okay. All right, so if I remember the last time, we were still working on chapter 2 assignments. I think I said to you guys that you should try the rest of the assignment at home. So before we move on to assignment number or chapter 3, I just want to find out if you guys have any questions concerning assignment chapter 2. Any questions about that? All right. Any questions on there in Zoom about assignment number 2? If not, then what I'm going to do is continue to discuss chapter 3. And as I said before, you guys need to, or should have, watched the videos for chapter 3. Chapter 3 is a relatively short chapter. Basically talking about matter, which you were introduced to earlier in chapter 1, if I remember correctly. And basically, matter is anything that has mass and volume. And some other terms that you were introduced to: properties, which would be the characteristic of a substance, things like color, taste, density, refractive index, and so on. And there are 2 types of properties. You have physical and you have chemical properties. Physical properties are those properties that can be observed without the substance undergoing a chemical reaction, while a chemical property is basically a property that can be observed as a result of a chemical reaction. And some examples are given here. Physical properties of chlorine, right? All of these can be observed without chlorine undergoing a chemical reaction. And then when it comes to chemical properties of chlorine, these are some a list of some of the properties, again, based on the definition. In this case, in order to observe these properties, the chlorine will have to undergo a reaction for that to be observed, right? Then if you understood the difference between physical and chemical properties, then you should be able to appreciate the difference between physical and chemical changes. And basically, it's the same basis. A physical change is one where the substance undergoes a change that you can observe, but in terms of its structure or its composition, it will remain unchanged, right? So for example, let's use a simple example. Water, as we all know, has a formula of H2O, right? And water can exist in the solid state as ice, in a liquid state, which is what we commonly call water, and also in the gaseous state, which we call the water vapor, right? In each of those instances, it is still H2O. The composition has not changed, right? So therefore, the transition from solid to liquid to gas, those are examples of what we call physical changes, because the changes are occurring in terms of the state of the substance, but the composition and the structure does not change, right? So these are just some other examples of physical changes. And then chemical changes are the ones where there is a change in the substance or new substances are created, all right? And the example here is given of the reaction between copper and oxygen to form copper 2 oxide. And basically, copper is by itself here, oxygen is by itself here. When they react upon heating, you're going to get copper 2 oxide, right? Copper 2 oxide is a different substance compared to these two. One can tell, for example, because of the color change. Copper normally has a reddish brown color, while copper 2 oxide is normally black, right? So one of the things that you look for in a chemical change or chemical reaction will be a color change, right? And that is demonstrated in this case right here. So let me just skip all this here. So a brief mention is made of chemical equations. We're going to get into that in more detail in a later chapter, but basically a chemical equation is a shorthand way of representing what's happening in a chemical reaction. So in this here, we're looking at the reaction of water. When you pass an electric current through it, it decomposes to form hydrogen and oxygen, right? So we can use the formulas to represent the reaction, right? Here we have the formula for water. Here we have the formula for hydrogen. Here we have the formula for oxygen on the other side, right? Typically, the reactants are on the left side, the products are on the right side of the equation. And in some cases, in fact, in most cases, you're going to have these numbers here. I won't talk about the significance of those numbers that appear before the formulas. That will be reserved for later on, right? But this is just a basic introduction to what a chemical equation is all about, right? Here's another example, the reaction between copper and oxygen to form copper 2 oxide. So this is the equation for the reaction. That's copper, that's oxygen, and this is copper 2 oxide, right? One key thing you need to remember about all chemical reactions, and this is true for physical changes as well, is that they all obey the law of conservation of mass. And basically what that law says is that there's no change in the total mass of a substance as you go from the reactants to products, right? So another way of stating it is that matter cannot be created nor destroyed in a chemical reaction. Here's a simple example that demonstrates this stuff. The reaction between sodium and sulfur to form sodium sulfide. Now, if you mix together 46 grams of sodium with 32.1 grams of sulfur and you heat it up, you're going to get 78.1 grams of sodium sulfide. If you take the mass of this here, you'll see that it's equal to the sum of the masses of the reactants, right? So this demonstrates that the mass of the reactants will be equal to the mass of the products, which means basically that as you go from the reactants, sodium and sulfur, to the product, sodium sulfide, no matter is created nor destroyed, right? Some definitions here: elements, a substance that cannot be broken down into simple substances. And the periodic table is basically the most comprehensive list of all the elements that are known. Some are naturally occurring, some are not natural, made by scientists, and most of those that are made by scientists are not stable, so therefore they will decompose to form other elements, right? We call it a nuclear reaction. So that's elements. As far as compounds are concerned, compounds are substances that can be broken down into simpler substances by chemical means, right? And that's very important, right? That last part, by chemical means, because elements can be broken down into simpler substances, but that would not be a chemical reaction, that would be a nuclear reaction. But elements cannot be broken down into simpler substances by chemical means, and the same is true for compounds. Well, not the same is true for compounds. Can be broken down into simple substances, but not by chemical means, all right? For example, water can be broken down into hydrogen and oxygen, and table salt, which is sodium chloride, can be broken down into sodium and chlorine. Okay, some other definitions here. Mixture of pure substances. A mixture is a physical combination of two or more substances, and the amounts, relatively speaking, can be varied. As far as mixtures are concerned, there are two types. You have homogeneous mixtures and heterogeneous mixtures, right? Homogeneous mixtures are uniform throughout, right? And an example of this would be sugar and water, right? So if you take sugar, which is a solid, add it to water, shake it up or stir it, and the sugar dissolves, you're going to end up with a homogeneous mixture, right? Which means that the sugar will be evenly dispersed throughout the volume of the water. And I'm quite sure you can name some other examples of homogeneous mixtures, such as any examples. It doesn't have to be anything complicated, anything from your everyday experiences. homogeneous mixtures? Should be that difficult. Mixture of two or more substances that where everything is just uniformly distributed.
Any soft drink?
Okay, soft drinks, yeah, because soft drinks would be a mixture of several things actually, including carbon dioxide, sugar, definitely, and flavor, coloring, and so on, right? So that's a good example. Can anybody tell me another example of a homogeneous mixture from your everyday interactions with life? Any other examples you can think of homogeneous mixture? And you guys out there in Zoom, feel free to chip in with your responses. Homogeneous mixtures, come on, think about it.
Could mashed potatoes be one?
I'm sorry, repeat that, speak up.
Could mashed potatoes be one?
Yeah, it's butter and water.
That's a good question. I would hesitate to describe that as homogeneous. Because I suspect that if you were to look closely at the particles, okay, let me just say this. One of the characteristics of a homogeneous mixture is that you cannot make a distinction between the different components of the mixture, right? And I suspect in the case of mashed potatoes, if you look at it more closely, like under a microscope or whatever, you probably can tell the difference between different parts. So I would hesitate about considering mashed potatoes as a homogeneous mixture. But I'm quite sure there are other examples you can think of. So let's hear them. I'm looking for 2 or 3 more examples. I'm sorry? A milkshake? Okay, so in the case of a milkshake, because it contains milk, and I know that milk is not homogeneous. It might look homogeneous, but if you look at it microscopically speaking, you'll see some sacs filled with fat, basically floating around the milk. So I wouldn't say milkshake would be homogeneous, a homogeneous mixture. So any other examples you can think of a homogeneous mixture? Yes, sir.
Lemon and water.
Lemon and water. Okay.
Lemon juice, I guess.
I guess so, if you can avoid the little sacks which contain the juice. Yeah, I would say so. Especially the ones that you buy in the store. What about gasoline? Right, gasoline is an example of a homogeneous mixture because I don't know if you know this, but gasoline is basically a mixture of hydrocarbons, right? So that's one example. Another example is the air we breathe, right? The air we breathe is also a mixture, which is homogeneous. The main component of which is nitrogen. If I remember correctly, nitrogen occupies about almost 80% of the air we breathe, and then oxygen is almost 20%, and then there's some other smaller amounts of other gases, right? Okay, so those are examples of homogeneous mixtures. Heterogeneous mixtures is the opposite, basically. Basically, heterogeneous mixtures are non-uniform, and you can tell the difference between the different components of the mixture, right? So an example that is given here is a mixture of sugar and fine white sand, right? That's an example of a heterogeneous mixture. Can you name some other examples of heterogeneous mixtures from your everyday life? Heterogeneous. Non-uniform mixture of 2 or more substances.
Oil and water.
Oil and water is a very good example of a heterogeneous mixture, right? If you add oil to water, what will happen? The water will be, you're going to form 2 layers. You're going to have the water below and the oil above, right? And of course, there will be a boundary between the two. So that's a very good example of a heterogeneous mixture. All right. Any other examples you can think of heterogeneous mixtures? One more example of a heterogeneous mixture. Salt and pepper, okay, that's a good example, yeah. So those are all examples of heterogeneous mixture. All right. So one problem that is faced by chemists all over the world, right? And this is true for people doing lab work as a student, up to people who are doing advanced research. And that is that very often they're faced with a problem of purifying compounds. In other words, you might have a compound you want to isolate from a mixture, right? It might have some impurities, right? So basically what the chemists have to contend with is, okay, how do I get rid of those impurities so I end up with a pure product, right? So basically some separation would have to take place, right? And in fact, I would say over the past maybe 3 decades, there has been a new discipline within chemistry called separation science. All these guys think about is how to separate mixtures, right? And the key thing that you need to basically determine when you're trying to separate a mixture is what would be the difference between what you're trying to get as a pure compound and the impurities. And basically your goal would be to exploit that difference in order to achieve that separation. So with that in mind, we're going to look at some simple examples. These are not, like high-level research type examples, but basically the principle will be the same. You have to exploit the difference between the substances in the mixture so that you end up with at least one of them being pure. Okay, so here are some situations that you could be faced with, right? How would you separate, and we're going to deal with the first one, salt from a salt solution, right? So you have a solution of salt in water, right? And your aim is to isolate the salt. How would you do that?
Boil the solution.
You heat the solution. No, why would you do that? Let's understand the rationale behind heating the solution. You're correct. You'd heat the solution, but what's the rationale behind it? Or better yet, let me ask this question. What would be the difference between the salt and water that would lead you to take that particular step?
Their boiling point.
Exactly. Water has a boiling point which is significantly lower than salt, right? The boiling point of water is 100 degrees Celsius. I don't know what the boiling point of salt is, but I know it's very high, right? So basically, as he suggested, you heat the solution. While you heat the solution, the temperature will rise until you get to the boiling point of the water, right? So the water will boil off, and basically, if you heat it long enough, basically you'll have no water left, and what will be left in the container would be the salt, all right? So basically, you're exploiting the boiling points of the two substances, the difference, I should say, in the boiling points of the two substances in order to achieve that separation. Very good, okay. What about the next one? A mixture of salt and sand. A mixture of salt and sand. How would you separate a mixture of salt and sand? And it won't be as simple as the first one.
Salt.
You dissolve what?
The salt.
The salt, right? How would you dissolve the salt? Right, so you add water to the mixture, right? So what is the difference between the salt and sand that you're exploiting when you decide to add the water to it? The difference between them would be what?
Same can dissolve the whole.
Exactly, the difference in their solubility in water, right? The water will selectively dissolve the salt and will not dissolve the sand, all right? But we're not finished yet. Now that we have that mixture, what's the next step? You add the water to the mixture, the water will dissolve the salt, but you still have the sand and the salt solution in the same container. So next question is, what's the next step? Because remember the aim is to separate the two, right?
Filter it.
Filter it, right, exactly. So in chemistry, and for those of you who have to do general chemistry, you'll do, well, not only general chemistry 1 and 2 and organic, you'll be doing a lot of these in the lab. So in chemistry, what we do is, as you said, you have your salt solution. You're going to have a funnel, right? In that funnel, so this is a funnel, and please forgive me, I'm not gifted artistic with this stuff. This might look weird. So that's your funnel. You're going to put inside it what we call a filter paper, right? So you're going to pour, in this particular case, your salt solution mixed with sand, right? And we all know what's going to happen, right? What's going to happen?
The salt solution, it's gonna,
The salt solution will pass through, so you're going to end up with your salt solution here. Now, the term that we use for describing the solution that passes through the filter paper, we call that the filtrate. All right? So basically, the filtrate, which would be the salt solution, will be collected down here, and up here, you're going to have your sand particles trapped on the filter paper. And then the next step would be what? Because now we have isolated the sand, but we still have the salt solution. So we boil it, just like we did in the previous question being asked. You boil the solution, dry the water off, and you end up with your salt, right? So that's how you separate a mixture of salt and sand. Okay. What about the third one? Ethanol and water. Now, ethanol is basically soluble in water, so it's going to be a solution, right? So you cannot, look at it and distinguish between the ethanol and the water. So the question now is, how would you separate such a mixture? Let me erase this here. How would you separate such a mixture?
You did that as well.
Okay,
I believe that one has an earlier boiling point.
you're absolutely correct. Ethanol has a low boiling point, and the water, if I remember correctly, ethanol is 78 degrees, and the water is 100 degrees Celsius, right? So heating is part of the process, but you have to do something else, or do something in addition. Because you're right, when you heat the mixture, you're going to get to the boiling point of the ethanol first, right? So the ethanol will start evaporating first. But what do you need? What do you need to do to trap those vapors that are produced when you hit that 78-degree mark?
we need to catch the vapor.
How would you, right, that's what I'm saying, how would you go about trapping that vapor?
Distill the vapor.
I'm sorry?
To distill the vapor.
That's the magic word I'm looking for, distillation. All right? How many of you are familiar with moonshine? Nope. That's basically illegal way of making alcohol from corn, if I remember correctly, right? Basically, distillation is involved in that process as well. So in the lab, we set up what is called a simple distillation apparatus. And again, you know what? Let me not draw this because I'm not good at these things. What I'm going to do is see if I can find a diagram of a simple distillation apparatus. Okay, which one shall I choose? Okay, let me choose this one right here. Make this bigger. Okay, so this is a, oops. I did that. Oh. Okay, let's see here if this works. Nope. Oh, I did that. Okay, I guess this is the best I can do. Okay, so this is the simple distillation apparatus right here. So imagine your ethanol and water is in this flask, right? So basically you have this adapter here, it's called the Y adapter. You have this thermometer here inserted, which is not necessary, but you might want to know what the temperature is based on your experiment. Then you have this condenser here. I'm going to say more about that. And then you have this here, I forgot the name of this adapter, but basically this adapter guides the condensed liquid into your container. This can be a flask or a beaker or something, right? This here, where it talks about nitrogen line, not necessary in all cases, but this is basically the setup. So let me describe what's happening here. So you're going to heat your mixture, as he correctly said, you're going to get to the boiling point of the ethanol first. So what should be emanating from this liquid here would be ethanol vapors, right? And the vapors will move up hit the thermometer so that you can register the temperature. And then the vapors have no other alternative but to go down this pathway right here. Now, here we have the condenser. The condenser is basically a glass tubing which is surrounded by an outer jacket. And that outer jacket has two outlets. You have one outlet here and one outlet here. And you notice it says here cold water in, cold water out, right? So basically in the lab, what you'll do is take a hose, attach it to your tap, and you're going to attach the other end to this outlet right here, and have another tube attached to this outlet and leading out into the sink, right? So basically when you turn on the tap, you're going to have a continuous flow of water on the outside of the inner tube, right? Now the purpose of the condenser, as the name suggests, is to condense the vapors that are coming into it. And the way that works is that when the vapors come in, now remember the water is circulating always in the outer jacket, right? So when the vapor comes in, the vapor will hit the inner walls of the tube. And because the walls are cooled by the water that is circulating around it, then the vapor will be converted to the liquid, right? It will condense. And then the condensed liquid will basically flow down here, and you can collect it down here in the flask at the other end of the setup. So that's basically how condensation, I'm sorry, not condensation. That's basically how distillation works. And this is a simple distillation apparatus. And you have other types of distillation depending on the type of mixture you're working with. This works best if the difference in the boiling points between the two liquids is more than 80 degrees, right? Now, if the difference is smaller, then you have to make some modification. For example, there is what they call fractional distillation. Let me see if I can find that one, which is similar, but you have another tube being added between the round bottom flask and the condenser. And that is for boiling point, that is for solutions where the boiling points are smaller or smaller in difference. Let me see, which one should I use? Okay. Let's see what this is. Okay, so this is it, right? So in the case of fractional distillation, oh, by the way, if not, this is if you're dealing with organic compounds here, using an open flame is a big no-no, just to let you know, all right? You should use a hot plate to heat organic solutions or organic mixtures, right? So in the case of fractional distillation, there's an additional piece here that is added, which is called a fractionating column, right? So we use this, everything else is pretty much the same. But we use this basically if the boiling points of solutions are closer together, the components. You have other types of distillation. You have vacuum distillation, you have steam distillation. Again, it all depends on the properties of the components in the mixture, all right? Okay, so that's it. Let me go back to the PowerPoint here. Okay, the last of these mixtures. How would you separate a mixture of oil and water? Now, we already know that this would be a heterogeneous mixture, right? So, how would you separate such a mixture?
Could you wait till they're separated from each other and just pour it out?
Well, would you successfully separate them if you just pour it out?
Well,
You'd have to be real skilled. But okay. To answer this question, there is a piece of glassware. Let me see if I can find it again online, known as a separator funnel. And basically, okay, so looks like a good one here. Okay, so this is what it looks like, right? Basically, you have a tap right here, all right? You have a stopper here, and let's say you have your heterogeneous mixtures, such as the one that's shown here, right? So basically, all you do is pour that mixture there, wait until the two layers separate, And then you just well, of course, you need to have something underneath here, like a beaker or a flask. And then you just simply turn on the tap and you drain the bottom layer until the boundary between the two layers get to where the tap is, turn it off. And that's basically how you achieve that separation, right? Another thing you could do, if it's a smaller amount of liquid mixture, is that you can take what we call a disposable pipette. Basically, it's a plastic piece of designed to suck up liquids. What you can do is take that and dip it into the top layer and pull up the liquid. Depending on how much you may need to do that, several times. And you can achieve the separation that way as well, all right? Okay, so, those are just some simple examples of separation. If you enroll in my lab for Chem 1 in the future, then there's one experiment that you will do which involves separation as well. So that's something for you guys to look forward to. So, with that said, let me give you assignment number 3 to work on, which is based on what we just covered. Go. And for you guys out there in Zoom, let me see if I published it. I'm not sure if I did. Hmm?
It's the scientific reason,
Is there?
not.
Oh, okay. Okay, so let me do that now. For you guys out there in Zoom, it's now published. All right, so you can work on that right now. And again, if you have any questions, let me know. Let me see who came in late, if at all. Anybody? Here, Kane is here. Barbara Lopez. Richie. Oh, and by the way, let me remind you of the event next week. I don't know if I made this announcement in class. I know I posted an announcement online about the STEM club, sponsoring an event talking about STEM careers. One person will be talking about the different STEM careers possible as career options. And another person will be from an organization known as the Institute of Human and Machine Cognition. And she will be talking about research about her organization and the type of internships that you can pursue there, right? So that will be next Wednesday at the Ocala campus. I forgot to include a link for Canvas, not Canvas, I'm sorry, Zoom, but I'll make sure that is available before that event. So it's going to be Wednesday, February 5th at 12:30. Okay, well, if you're finished, what you're gonna do is submit it online. I've opened up a Dropbox. Let me just check to make sure everything's in order. And the deadline for submission, if you have not finished here, would be, Thursday. So to give you some time to make sure everything is ready. Let me also say that, according to the syllabus, your first test should be next week, but I've decided to put that off until the week following. The reason why is because I want to be able to, because I think right now, you guys have submitted assignment number 2, right? Or about to, I think the deadline is today, right?
Yes.
So, I have to grade that, and then I have to grade assignment 3, and get it back to you guys, so that you guys can review. I don't think, you know, next week is enough time for you to, prepare for your test based on those 3 assignments. So I'm just gonna put off that test until the week after next, right? So for now, assignments 2 and 3 will be due. Assignment 2 is due today, assignment 3 is due on Thursday. No, that's pretty much it. Oh, and also make sure you watch the videos for next week, for chapter 4. We're to post an announcement as well.
Said, well, that. Next,
Let me make sure that video is published.
we're not having the test next week, it's gonna be.
Okay, so I've just published the videos for chapter 4. So make sure you watch those videos in preparation for next class. Yes, sir.
Is it test from chapter 1 to 4?
No, 1 to 3.
Oh,
Right. Yeah, you do. Yes, so yeah, you'd have to, I think the way it works is that you go to their website and you make an appointment. I'm gonna say more about it like next week, just to let you know, but that's basically how it works. And it can be any one of the testing centers between Levy here and
Does it
Okay.
have to be on that exact day?
I'm sorry?
Does it have to be on that exact day?
No, I'm gonna give you a week.
Okay.
And then you can choose whichever day, of course, depending on your schedule. I think they have a rule about not scheduling too late. You remember exactly like 30 minutes from closing or something. Yes, yes, sir.
I use like a periodic table of elements.
Oh, yeah, I'll provide all, you see that table, that document that I have in Canvas? With the periodic table, and that will be available to you guys during the test. I was kind of confused. With that, I wasn't sure. That called about, that's you?
Yeah, right. It's like,
Um. So you were present, I remember you were present all the classes, right?
yeah,
Okay, but I don't know, keep that in mind, and I think there was an issue with an assignment,
for me,
because there's another, well, for one, I was going by Barbara. But there's another Lopez registered in the class, I don't know if that was you, or?
no, that's. Oh, guys.
Oh, okay, alright, okay, alright. Alright, so what I'll do, I think it's some, in my, on my desk, I don't have it, so I'll have to look into it,
Okay, thank you.
alright,
Have a good one.
you too. Yeah, you too.
Hello?
Yep.
Mr. Pete,
Hold on 1
or
minute,
Mr. Professor Nestle?
yes, sir,
Oh, is it, trying to,
uh,
sorry. Is the class over?
uh, pretty much, unless you have a question to ask.
Oh, I just had to, ask you about the resubmission about assignment, 1.
I'm sorry, repeat that?
I have to ask you a question about, resubmission 1, or the assignment for 1. I was asking if I can still resubmit. I had issues with it a bit.
Assignment number 1,
Yeah.
hold on, what kind of issue do you have?
Oh, no, it was just resubmission. I know you, emailed me that I can resubmit it, but you would
Oh,
take
okay.
off points.
So have you emailed it, have you, okay, well, what you should do is email the assignment to me as an attachment,
Okay, all right then.
alright?
Yes, sir. Also, you have me down for attendance, right?
Let me check and see. Camacho, yes, sir, I do have
Okay.
it,
Yes, sir. All right. Thank you.
alright,
All
I
right.
think I'll sign off now, because there's nobody here, so,
Oh, okay. There's no one there.
no, but it's basically there.
Okay, so I can leave, right?
Yes, sir,
All right. Have a good day. Thank you.
yeah, you too, take care.
Hey, take it.